Good morning, students. Today we will recall the bare category theorem, and then we will see some of its consequences. So, let me first state bare category theorem. So there's many versions of this. So let me first state this. So suppose XD is a complete metric space. And let Vn be a collection of open dense subsets of X. Then the conclusion is that if you look at the intersection of these VNs, this will again be dense. So then this is also dense in X. So what it says is that if you have a countable collection of open and dense subsets, then their intersection is again dense. And this is true for complete metric space. This is also true for if you assume a compact Hausdorff space or locally compact Hausdorff space, then also the same conclusion is true. But since we will be dealing with only norm-linear spaces, so this version is good enough for us. So we are assuming that there is a complete metric space, and then if I take any countable collection of open dense subsets, then the intersection is again dense in X. So I assume that you would have seen the proof of this bare category theorem in some course like real analysis course. So I'll skip the proof. Anyway, the proof is not very difficult. So if you don't remember, then you can go back and look at the proof. Basically, you have to use the completeness of this metric space. So you have to somehow get a Cauchy sequence and then use that Cauchy sequence must converge, and that way you can prove that this intersection is dense. So I'll not do that because that will take a little time. But there are some equivalent ways in which this can be stated also. So many times, like what we need here, it is saying that the intersection is dense in X. So in particular, the intersection of these VNs will be a non-empty set. So many times that is what is used. If you have any like non-empty complete metric space, and if you take collection of open dense subsets, countable collection, then their intersection is also dense. Also, I mean, of course, you can see that this is not true for any metric space. So if you don't assume completeness, then this thing is maybe false. So you can have in incomplete metric space, you can have that the intersection of this thing is dense. So For example, I mean, you can take x to be the set of all rational numbers with the usual metric induced from R. And then if you take, because rationals are countable, so if you take the complement of singletons, that will be a countable collection of open and dense subsets. But if you look at the intersection of all of those, that is just the empty set. So completeness is important here. So okay, let me mention some definitions also. So recall. A subset, say A of a topological space. If you want, you can only assume metric space. So a subset A of a topological space, say X, is said to be nowhere dense if the interior of the closure of A is empty. Nowhere dense means that the interior of the closure of that set is empty set. And a set is said to be of first category if it can be written as a countable union of nowhere dense subsets. So if you have any topological space, and then if a subset can be written as a countable union of nowhere dense subset, then it is called the first category. And if it is not of first category, then it will be called of second category. The set is said to be of second category if it is not of first category. Which means that second category means that it cannot be written as a countable union of nowhere dense subsets. So note that now we can state this bare category theorem in terms of the second category. So what this theorem is equivalent to saying that uh, a complete metric space is of second category. Write this remark. The bare category theorem, and that is why it is called bare category theorem. So the bare category theorem is equivalent to the following. Every complete metric space is of the second category. Right. So this should be clear. So to show that you have to show that if we have a complete metric space, then it cannot be written as countable union of nowhere dense subsets. So suppose X can be written as the union of countable union of nowhere dense sets. Then if you take the complement, then you will get that the countable intersection of open dense sets will become empty. So that will contradict this bare category theorem. Also, maybe I'll give one more definition. Now, G delta set. So, a countable intersection of open sets in a topological space is called a G delta set. G delta set means that it is countable intersection of open sets. Of course, countable intersection of open set need not be open. So, you can have a G delta set which is not open. So, if you see here, VNs are open sets. So, this intersection of VN, this is a countable intersection of open sets. So, this is a G delta set. So, here we are getting a dense G delta set. So, one corollary of this bare category theorem is that if we have any complete metric space, and if we have a countable collection of dense G delta set, then that is again a dense G delta set. So the intersection of any countable collection of dense G delta set is again a dense G delta set. So the intersection of countable collection of G delta set is of course G delta, because every set is countable intersection of open sets, and there are countably many such things. So if you take the we know that countable union of countable set is countable. So if you take the intersection of all those open sets, that will be the intersection. So that is a G delta set. And to say that if these are dense G delta set, then the intersection is again dense. That follows by this bare category theorem, because you have only countable collection of open dense sets. So that intersection is dense, that is by this bare category theorem. Okay, so let me mention some consequences of this bare category theorem. So, I mean, this theorem, it is not very difficult to prove, but this has lot of applications. So that is why it is very useful. So one thing we will do for Banach space. So let me write this as a theorem. So let X with some norm be an infinite dimensional Banach space. Then X has an uncountable Hamel basis. Or I can say that every basis of X has to be uncountable, because any basis has the same cardinality. So let me say this, that then X cannot have a countable Hamel basis. So notice that here we are talking about Hamel basis. So oh, that is in the sense of linear algebra, because we have also studied about Schroeder basis, and we can have countable Schroeder basis, for example, for LP spaces we have seen. So this is we are talking about Hamel basis. It has to be uncountable. So how to prove this? Am I audible? Hello.
Yes, sir. Yeah.
Okay. So suppose B equal to, let's call V1, V2, Vn dot 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 B countable thermal basis of X. So because we have that X is infinite dimensional, B E has to be an infinite set. So since dimension of X is equal to infinity, B is an infinite set. Because if you take finite dimensional, then of course it has a finite Hemmel basis. So or you can have finite dimensional Banach space, but for infinite dimensional, we are saying that the basis has to be uncountable. So if we have this, now let's write. So let Fn is equal to the span of V1, V2 up to Vn. So we are looking at the linear span of the first n vectors V1, V2, Vn. Then what can we say about Vn? So then what can we say about this Fn? Then Fn is a proper subspace of X. Right, because X is infinite dimensional, this Fn will be a proper subspace of X, and also Fn is closed, because this is finite dimensional. Any finite dimensional subspace of Banach space has to be closed because it is complete and therefore it is closed. So we have, but this is a closed proper subspace, and because this is a proper subspace, therefore its interior is empty. So note that since Fn is a proper subspace, its interior must be empty. Maybe this you can take as an exercise. So any proper subspace of non-linear space must have empty interior. You prove it by contradiction. Suppose that uh, the interior is non-empty, then there exists an open ball contained inside this Fn, and if you have an open ball which is say contained inside this because this is a subspace, so you can show that there exists an open ball centered at the origin which is contained inside Fn, and because it is a subspace, if you have an open ball, then you can multiply by scalar, and then that way you can prove that every point will be in Fn, but that will contradict that this is a proper subspace. So that is why this is true. So therefore, we get that Fn. So therefore, each Fn is a nowhere dense subset of X. Right, because nowhere dense, the definition was that the interior of its closure is empty. Because this is a closed set, the interior of closure is same as interior of Fn, which is empty. So therefore, these are all nowhere dense subsets. But if B is a basis for X, then we have since B equal to V1, V2, this is a Hamel basis of X. X is nothing but the union of Fn n equal to 1 to infinity. Right, this is just the definition of basis, because the any point, any vector v in X, we know that it is a finite linear combination of these basis vectors. So that means that if we take any v in X, then v is equal to summation of Ci vi for I equal to 1 to n for some n. So that will imply that X belongs to some Fn. So X is equal to union of Fn, but this contradicts the bare category theorem. So since X is a complete metric space, this contradicts the bare category theorem. Is it okay? So this shows that if we have any infinite dimensional complete nonlinear space, then uh, its Hamel basis must be uncountable. So you can use this to solve this problem also. So let me give this exercise. So suppose we take this the sequence space. So or we denoted by C00. This is all sequence which are eventually zero. Xi's are set in R or C. So this is a vector space. Now, can we define any norm on this such that this becomes complete? So let me write this as X. or let's call this C00. So that there is no norm on C00 such that it becomes a Banach space. So it is just applying the previous result, because the C00, this has a countable basis. If you take E1, E2, E3 and so on, that forms a basis for C00. And if and that is an infinite dimensional, so you get a countable infinite basis. But if there is some norm such that this is a Banach space, then we know that it cannot have any countably infinite basis, and therefore you cannot have any norm with respect to which this will become a Banach space. Similarly, if you take the polynomial space, then you cannot define any norm such that it becomes complete. Okay, so now let us come to the some important theorems of using this bare category theorem that we can prove for Banach space. Write what is called Banach-Steinhaus theorem. Let V be a Banach space and let W be a non-linear space. Let I be an arbitrary indexing set. So this I can be countable or uncountable, anything. So we take any indexing set, and for each I in I, let Ti belongs to BVW. So Ti is a bounded linear operator from V to W. Then either the supremum of norm of Ti, I belonging to I, this is finite, or supremum of norm Ti of X, I in I, this is infinity for all X belonging to some G delta set in V. So for all X belonging to some G delta set. So let's try to understand what this theorem is saying. So we have a collection of bounded linear operator from V to W. These are TIs. And V is assumed to be a complete norm-linear space. W can be any norm-linear space. Then the conclusion is that either there exists some G delta set such that for all x in that G delta set, supremum of norm Tix is equal to infinity, or you have supremum of norm Ti is finite, which will mean that norm Ti is actually bounded. So norm Ti will be less than equal to some constant for every I. So in particular, when you will get that, suppose Ti is such that this is pointwise bounded, which means that suppose supremum of norm Ti of x, this is for every x, suppose that this supremum is finite, then that would imply that supremum of norm Ti will be finite. So that is saying that if this is a collection of operators, bounded linear operators, which are like pointwise bounded, then it is bounded. So that I'll state after this theorem. So that is why this is also called principle of uniform boundedness. So that will be the next theorem. First, let me prove this one. So for each x in V, define phi of x is equal to supremum of norm Ti of x for I in I. So, I mean, this can be infinity also. So we are writing this phi of x as supremum of norm Ti of x, and let Vn equal to all x in V such that phi of x is bigger than n. Vn consists of all those vectors such that phi x is bigger than n. So this is for n belonging to n. We define Vn. So because TIs are continuous functions, and norm is also continuous, so this Vn, note that Vn is open since Ti is continuous for all I. So using that, you can see that Vn is continuous. Vn is open for every n. Also, we have that this V Okay, so okay, so assume that there exists some n such that Vn is not dense in V. So suppose that for some n, Vn is not dense in V, then what do we get? So then there exists X naught and R positive such that the open ball such that B of X naught R, this is the not intersecting this Vn. Right? Because Vn is not dense, so that means that there exists some open ball which does not intersect with Vn. So that is this. If we look at X plus X naught, this is not in Vn if norm X is less than equal to say R. So for any X with norm X less than equal to R, X plus X naught, because this is in the closed ball of radius R, so centered at X naught, and because that does not belong to Vn, so X plus X naught does not belong to Vn. So what does this imply? By the definition of Vn, Vn consists of all x such that phi of x is bigger than n. So therefore, this is not in Vn implies that phi of x plus x naught is less than equal to n if norm x is less than equal to R. Is it okay? But what does this imply? Phi x was defined to be supremum of norm Ti of x. So this means that norm of Ti of x plus x naught, this is less than equal to n if norm x is less than equal to R. This is true for every I in I. Norm Ti of x plus x naught is less than equal to n. So what can we say about the norm Ti of x? This by triangle inequality and linearity of Ti can be written as Ti of x plus x naught norm plus norm of Ti of x naught, which is less than equal to n plus n to n if norm x is less than equal to R. Because Ti of x plus x naught norm is less than equal to n, and Ti of x naught is Ti of 0 plus x naught, so that is also less than equal to n. So norm Tix will be less than equal to 2n if norm x is less than equal to r. And this will imply that norm of Ti is bounded by. So this implies norm Ti, because the norm Ti is equal to supremum of norm Tix by norm x for x not equal to 0. So norm Ti Ex is less than equal to 2n if norm x is less than equal to r. So this will be E less than equal to 2n by r.
Like, how do we know that this supremum occurs at norm x equal to r?
Sorry?
Here we are taking a supremum over all points in this closed ball.
Right.
And we know that
No, okay.
so
So
denominator is less than equal to r. So
if you want, I can write this thing as this, then it will be clear to you. So let's write this as the supremum of norm Ti of x for norm x less than equal to 1. Right? This is also norm Ti.
yes, yeah, I think now I get it.
Now it is clear, right? Because norm x less than equal to r means that norm of if norm x is less than equal to 1, then norm of r times x will be less than equal to norm r, less than equal to r, and then you know that Ti of r times x, that is less than equal to 2n, and therefore norm of Ti of x will be less than equal to 2n by r. So this is true for every I. So for all I in I. So this means that supremum of norm Ti is less than equal to 2n by r. So this is one possibility that is saying that supremum of norm Ti is finite. So this is less than infinity. If this is not true, so this was under the assumption that there exists some n for which Vn is not dense in V. Otherwise, it can happen that each Vn is dense in V. So the other possibility is that each Vn is dense in V. So what does that imply? If each Vn is dense in V, then we already have that each Vn is open also. So we get that each Vn is open dense subset of V, and then the bare category theorem will imply that intersection of Vn is also dense. So each Vn is open dense. So by the bare category theorem, intersection of Vn, this is dense in V. Let's call this set as G. So G equal to intersection of Vn is dense in V. So what happens? So then G is a dense G delta set. And what happens for X belonging to G, and for every X belonging to G, phi of X belongs to Vn, but Vn was that phi of X is bigger than N, so phi of X will be bigger than N for every N in N. So this implies that phi of X is equal to infinity. So phi of X is in infinity for every X in G. So that is same thing as saying that is the supremum of norm Ti of X. This is equal to infinity for all X belonging to G. So this was the other thing, that there exists some G delta set such that for every X in that, supremum of norm Tix is equal to infinity. So an immediate corollary to this is called principle of uniform boundedness. This says that if V is a Banach space and W is a non-linear space, and if Ti belongs to BVW for I in I, such that supremum of norm Tix, this is finite for every X in V, then there exists M such that supremum of norm Ti is less than equal to M. Right, so this says that if our Ti is such that uh, this collection Ti of bounded linear operator is such that it is pointwise bounded. That means that for any given X, if you look at a supremum of norm Ti of X, that is less than infinity, which is same thing as saying that for every X, norm Ti of X will be less than equal to some constant which may depend on X, because here when we say that this is finite, it can be that norm Ti of X is less than equal to some, say, mi m of X, where m of X is some constant. For every I, this is true. Then it is saying that norm Ti will be less than equal to M for every I. So this follows immediately from the previous theorem, because if supremum of norm Tix is less than infinity for every X, then that means that we cannot have any G delta set where supremum of norm Tix is equal to infinity, right? Because For every Ax, we know that it is less than infinity. So therefore, we must have supremum of norm Ti is finite, which is same thing as saying that there is some constant such that uh, supremum norm Ti is less than equal to n. So this is the principle of uniform boundedness, and I don't have time, so I'll in the next class I'll show some more like application of this Banach-Steinhaus theorem, and then we will discuss the open mapping theorem and then closed graph theorem. For that, again, this bare category theorem will be useful. Let me stop here. Any question?
So actually, I had one question from like an earlier lecture.
Yeah,
Like when we discussed this thing on embedding, we said that like a non-linear space in general, it need not be Banach, but we know that the double dual like V star star is always
Banach.
a
Yeah,
Banach space. Like when we consider the embedding, it might not always be onto. Like it might just
right,
like it's an isomorphism, but it's onto some subspace of V star star.
right.
Like I was thinking that like is it true that like the image of that embedding, will it be dense in V star star, or like can it be cases where it need not be dense also? Like suppose if we consider the completion of that embedding, completion of that image of the embedding, will we always get V star star, or uh, even that completion might also be a proper subset?
I think it need not be dense also. So, or suppose you take, for example, uh, yeah. So, for example, if you take this C00, right?
Uh-huh.
So, what is C00 double star? If you think so,
C00 double star. So first, if we find C00 star,
right,
uh, it will be like if we consider that Fy, like we had defined, like given a y, we could define f of y as fy at x as sum over I xi yi, and so the star will consist of, will be isomorphic to those y's where for every for every ultimately zero sequence, eventually zero sequence, we have that the dot product is bounded. Uh, uh,
or okay, let me maybe take
like how do we C00 has sup norm, no?
right, right. So it is as a subspace of L infinity. Or let's consider C0. So C0, if you take its dual, you can show that that is isometrically isomorphic to L1, right? This I
Okay.
gave as one of the problem in tutorial set 3 of,
Right.
right? So dual of C0 is L1. So C0 double star will become L infinity, right?
Yes,
So,
yes.
so that is a Banach space. So but C0
C0 will not be dense in L infinity because C0 the sequences converge to 0, and if I consider any
Right.
sequence which converges to
Then
non-zero, I
that
can
again
find
will
a normal
convert to zero. Right. Right. So,
around it.
so this will give you a counter example, right? So
Yes.
C0 is not dense in L infinity, so you get that C0 is not dense in its double dual.
Okay. Okay. So like if the suppose if there is some vector space which is like which is dense in V star star, say, but it's not like whose embedding in V star star is a dense subset of V star star, but overall it's not equal to V star star. So it's not reflexive as such, but do we give any special significance to such vector spaces? Which whose image is dense, but it need not be as such reflexive fully.
Uh,
Because not like if it's not always dense, which means that even being dense in V star star is now a special property. So do we give any significance? Like, are there any results which are based on like being being dense in V star star? Like, if it's helpful.
yeah, I don't know, but yeah, that is a good thing to think of. That even if it is not a Banach space, you can think of the double dual being dense in. Uh, so that is space being dense in its double dual. So I don't know. Maybe people might have considered, but right now I'm not aware of whether like it will give you something interesting or not.
Ah, yes. Like for rationals, if I consider the set of rationals as a vector space over rationals,
Right.
then if I take its double dual, will we get okay? Yeah, sorry. Yeah, I think I'm too much digressing. Okay, yeah,
Yeah.
thank you.
So you think about it, and then like if you think that something, right now, no, I am not aware because when we study about these reflexive spaces, we always like consider only Banach spaces and do that.
Okay.
But yeah, one may think what you are doing and define something like that. But I don't know whether like that gives something interesting, whether it has been studied or not.
Okay. Thank you.
So okay, let me stop then. And you must be knowing, all of you, that the exam will be on Sunday. So, so in the schedule, it is given that the exam should end by 11 o'clock. So we will start the a minor exam, midterm exam at 9 o'clock, and probably it will be for 1.5 hours, 30 marks. So 9 till 10:30, and then you will get some time to like upload the answer sheets on Gradescope. So anyway, all the information I'll send an email and inform that those things. But you can be prepared that Sunday 9 o'clock will be the exam.